A very good morning to all. Let us continue our discussion of the subject discrete mathematics. Today's topic being discussed is closures, relations. Under relations, this topic we are discussing. As usual, the material we are using, we are citing them. For example, today's learning material is derived from prescribed textbook by Kenneth H. Rosen, Discrete Mathematics and its Application, McGraw-Hill publication. Also, few links I have used called as math24.net, rutgers.edu, cs.fsu.edu. So let us start with reflexive closure. For reflexive closure, let us remember reflexive relation from the previous discussion. So we'll directly jump to the example. We need to check whether R1 is reflexive or R2 is reflexive. So, and we know that R1 is not reflexive here, okay, because there is no 3 comma 3 relationship in R1. Because what is the definition of reflexive? A comma A belongs to R for all A belonging to A. Okay. It means every element in the relation is related to itself. So here 3 is not related to itself, so hence R1 is not reflexive. In case of R2, you can say every element is related to itself. 1 is related to 1, 2 to 2, 3 to 3. So here we can say that in this relation is the example of reflexive relation. Once we could connect with a reflexive relation, let us look at reflexive closure. Now, how do I find the reflexive closure? It is called as the smallest reflexive relation RR on A that contains R. The smallest relation means what? Fewest number of ordered pairs. How do I obtain the reflexive relation? I have to go on adding element A comma A to the relation R for all A belonging to A. This can be written as R of R is equal to R union I, where I is the identity relation, which is given by I is equal to A comma A for all A belonging to A. We'll take the example for simpler understanding. This is my relation. R is equal to these pairs 1 comma 2, 2 comma 4, 3 comma 3, 4 comma 2. And this is my set 1 comma 2 comma 3 comma 4. And I know that this is not reflexive. Okay. So what do I do to make it reflexive closure? Okay. So for that I had to add identity I. Okay. So here identity is given by 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. So basically what I am doing is to this relation I am adding this 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. So R union I. So that's what is the definition of closure of reflexive closure. Okay, R union I. So it has fewest number of ordered pairs. Got this? Now, how do I solve this use in the matrix form? First, what I'll do is I'll take my original matrix. This matrix is derived from this relation 1 comma 2, 2 comma 4, 3 comma 3, 4 comma 2. This is 1 comma 2, 3 comma 4. Wait, this is 1 comma 2, 2 comma 4, 3 comma 3 and 4 comma 2. This is 3 comma 3 and this is 4 comma 2. So this is my original matrix which is derived from this relation. To this I am adding the identity matrix. Okay, all the diagonal elements are 1. So when I am adding them, I can see that this is the derived matrix. Now using this derived matrix I can draw a digraph, okay? Or I can just add self loops to all the vertices. I can just add self loop to all the vertices. So what I can conclude is that, give me a minute. It's okay. How I obtained this reflexive closure is I added this loop which were missing. So that I need to remember. So what it is saying for reflexive closure, what needs to be done? Add loops to all vertices on the digraph representation of R. The reflexive closure is denoted by this R of R, which is R union this delta. So there is one more definition here, reflexive closure. This delta is called as a diagonal relation on A. So how do I put reflexive closure? R union delta. Why it is reflexive? Since A comma A belongs to delta, which is a subset of R, union delta for every A belonging to A. Let us go for the next one, symmetric closure. So symmetric closure of R denoted by S of R. It is a relation R union R inverse, where R to the power of minus 1 is the inverse of the relation. So I should remember that if I want a symmetric closure, I'll take the inverse of the relation and make a union of the inverse with the actual relation. How do I take the inverse of a relation? I need to reverse all the arcs in the digraph, or if it is matrix representation, I need to take the transpose of the matrix. So how do I obtain symmetric closure is I go on adding B comma A to the relation R for each pair of A comma B which belongs to the relation. So remember this, go on adding B comma A. And in terms of relation operations, symmetric closure is R union R inverse or R union R transpose if it is matrix representation. Let us take our example. Okay, this is our set consists of 1 2 3 4, and this is our relation 1 comma 2 1 comma 3 2 comma 2 2 comma 4 4 comma 3. Why it is not symmetric? Because I know that you don't have these non-reflexive elements. 1 comma 2 doesn't have 2 comma 1. 1 comma 3 doesn't have 3 comma 1. 2 comma 4 doesn't have 4 comma 2, and 4 comma 3 doesn't have 3 comma 4, which means I need to add these missing reverse elements, that is 2 comma 1 3 comma 1 4 comma 2 3 comma 4. So I take first the union of adding the missing elements with the actual relation. So this becomes my relation. Now for matrix representation, what do I do? This is my matrix representation of the relation. This is 1 comma 2, 1 comma 3, 2 comma 2, 2 comma 4 and 4 comma 3. So I have to take the inverse of this. I have to take the inverse of this means what I did, I just found out the transpose of this matrix. How do I find the transpose of the matrix? Okay, so these rows are being converted into columns. Simple 0 1 1 0. This is 0 1 1 0. 0 1 0 1. This is 0 1 0 1. All zeros, all zeros. 0 0 1 0, 0 0 1 0. So once I got the transpose of the matrix, add the transpose with the original. So this is my original, this is my transpose. So once I add them, it comes to this 0 1 1 0 1 1 0 1, 1 0 0 1 and 0 1 1 0. It's easy, right? So I can find the digraph or draw the digraph for symmetric closure by adding edge in the reverse direction. See here. There was an edge from 1 to 2, but missing edge was 2 comma 1, which is added. There was an edge from 1 to 3, the missing edge 3 comma 1 is added. There was an edge from 4 to 3, the missing edge 3 comma 4 is added. There was edge from 2 to 4, the missing edge 4 to 2 is added. Sorry. So that was all about symmetric closure. Let us go for the transitive closure. For transitive closure, first let us take the exam. Okay. As usual, this is my set. Set A consists of 1, 2, 3, and this is my relationship for the set 1, 2, 2, 2, 2, 3, 3, 3, 3. This is not transitive. Okay. Why it is not transitive? Because 1, 2 is there, 2, 3 is there, but 1, 3 is not there for closure. Is it not? So it means what? We need to add this missing element 1, 3. So for this is the symbol for transitive closure, T of R. So R union the missing element 1, 3. So just take the relation R 1, 2, 2, 2, 2, 3, 3, 3 union with 1, 3. So this becomes my new relation. How do I get the digraph? So I need to check the edges. Okay. And I see that this missing edge is added 1, 3. See 1, 2 is there, 2, 3 is there, but 1, 3 was missing, that was added. For matrix representation for transitive closure, what do I do? This is my matrix, okay? Because 1, 2 is there, 2, 2, 2, 3 and 3, 4. 3, 3. 1, 2, 2, 2, 2, 3, 3, 3. Now I need to find the connectivity relation R star, which is determined by the representation of the expression R union R square union R cube. So how do I find R square? Take the original matrix, multiply it by the same matrix. So do the multiplication, matrix multiplication, you will be deriving this 0, 1, 1, 0, 1, 1, 0, 0, 1. Now this becomes your R square. R square again multiply with the original matrix, you will be getting the R cube. So you got this 0, 1, 1, 0, 1, 1, 0, 0, 1. And you can see that matrix R square and matrix R cube are same, equivalent. So my connectivity relation R star can be found out using R union R square. So I know R is there and I know R square is there. So R union R square, I'll be just putting the addition, and I can see here this is my new relation. If I convert this matrix into a roster form, I'll be getting this 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. So the missing element 1, 3 is highlighted here in red. So as far as transitive closures are concerned, okay, how do I put? I need to understand the concept of path in transitive closures. Is it not? So there is a relation called as R. There is a set called as A. There are two elements A comma B which belong to A. Okay. There is a path from A to B with a length n. Okay. But this path with length is actually a sequence of ordered paired A comma x1, x1 comma x2, x2 comma x3, xn minus 1 comma b. Okay. Here n is a non-negative integer. Same thing we'll take, let us say this is my set 1, 2, 3, 4 and this is my relation 1, 2, 2, 4, 4, 3. So now these are the pairs 1, 2, 2, 4, 4, 3. These are the paths also, but their length is 1. Their length is 1. But we also have pairs like 1, 2 and 2, 4 of length 2. And there is also a path called as 2, 4, 4, 3, and length is 2. But the entire relationship has the path length of n, 3. So the value of n is 3. Now, what the theorem says is that R is the relation, A is the set, A is an element belonging to set A, B is an element belonging to set A. Then there is a path of length n from A to B if and only if A comma B belong to Rn for every positive integer n. Okay, so it should be part of that Rn. As far as connectivity relation goes, which is denoted by R star, it has all the R dot pairs such that there is a path in R from A to B. Okay, this is my connectivity relation which is found out using the union of the set. Now the cardinality of the set A is say n. Then the connectivity relation is given by R star which is equal to R union R square union R cube union Rn. Okay. What is a transitive closure? It is just a connective relation R star. So this is all about closures. Very simple examples which are derived from multiple sources. Thank you.